All right, gang, so let's, what we're doing here is for the first observation, for example, from LSS, IQ, and EST with a read of 55. Using this student's LSS, IQ, and EST, we would have predicted this student to have a, a predicted read of 66.48. Well, notice the residual is negative 11.5 because the read is about 11 units less than what we predicted. Now, this gives you a really nice way to look at your data. I like to look at the residuals, any residuals that seem to be, unusually high or unusually low. For example, this one kind of concerns me. This student had a reading level of 10, yet our model predicted this person's reading level to be 60. So if this was a data set that that I was truly interested in from an academic perspective, I would suspect that may be a typo. And I think that would be something that I would want to investigate. If it's not, this could clearly represent some sort of learning disability, because when you have, a huge discrepancy between the person's aptitude and their achievement, then that typically indicates a learning disability. So I don't know what's going on with this guy right here, or girl. I have no idea gender, but we could certainly look. I don't know if there's any others that large or not. So anyway, gang, we've got the residuals. So the next thing I want to do, just to illustrate, is I want to do the variance covariance matrix for the our errors / residuals. Now, this is found is found by taking our mean square error times our identity matrix minus our hat matrix. So the first thing we got to do is we've got to create a hat matrix, and we've got to we got to create our identity matrix, and we got to use our hat matrix. So the easiest way to do the identity matrix is to do diagonal 30. And what this is going to do is it's going to create a 30 by 30 matrix, but it's going to create on the diagonals our ones, which is exactly what we need for an identity matrix. So next thing I'm going to do is I'm going to just store this as like n, or whatever you want, and I'm going to take the identity matrix minus the hat matrix. Well, it's a day of just messing up, isn't it? And we get our n matrix here. Now, I've got to multiply that by the mean square error, and the mean square error was way back here someplace. So the mean square error was 342. Well, I really didn't need to go back there. All I need to do is just do mean square error, right? So I need to take, so I'm going to do standard error for the residuals. And I'm going to take 342.6867. And I'm going to multiply what I call that the n matrix. And we get the the standard errors for the residuals. Okay. Now, what I want to move into now is I want to move into creating our Anova. And I want to get out of R, and I want to get back into the blackboard here. So, gang, what I'm going to do here is I ultimately want to be able to create So we're going to have our regression. We're going to have our error. Well, this is typically referred to as residual. And I want my total. So the first thing we'll have is our sum of squares. Next thing we'll have is our degrees of freedom. Next thing we'll end up with is our mean square term. Next thing we'll end up with is the F and the p-value. Okay? Now, we already know that the sum of squares for the error is 8909.853. So I'm going to make a note of that on the blackboard under sum of squares for the residual. Now, we already know that the degrees of freedom for this were n minus p or n minus k minus 1. And we know that that is 26. And when we take the sum of squares divided by 26, we get 342.7. Now, just so we're all on the same page here, you can see what I've done is this right here. Now, arguably, some people think it doesn't matter. Some people think the total. Some people think the regression sum of squares is easier to find. I mean, you know, we're not doing it by hand, so I don't think it's a major deal. So I'm just going to find the total sum of squares. And remember, if we can find one of these, all we have to do is subtract the residual sum of squares from the total to get the sum of squares for the regression. So let's go do that. So guys, what I'm going to do now is I'm going to do the sum of squares for the total. And the sum of squares for the total takes the transpose for y times y. I'll tell you what, I don't think it would be an issue if I did that, but because I am overprotective of stuff like that, I'm going to put that in parentheses. Then I'm going to go minus, so we have 1 over n, so I need to do 1 over 30 times. Then I need parentheses transpose for y times our J matrix. Darn it, darn it, darn it. Forgot to do the J matrix. All right. Forgot all about that. So gang, let's create, sorry about that. Let's create the J matrix. So guys, just remember the J matrix is a matrix of just all ones. So I would create the J matrix here. And I would probably go repeat, let's do this, C, repeat integer 1 30 times. In row would be equal to 30. In column would be equal to 30 by row equal false. So my J matrix is just this enormous n by n matrix of all ones. So guys, what I can do now is come in and do my sum of squares for the total. And now I'm going to do transpose y times y. minus 1 divided by 30 times the product of transpose y J matrix y. So our sum of squares for the total is going to be 15,771.2. So guys, we can clearly do our sum of squares for regression by just taking 15, well, our sum of squares total minus sum of squares for our residuals. So gang, our sum of squares for the regression is going to be 61.3. Now let's go back over to the board. Guys, our degrees of freedom for the regression term are either p minus 1 or k, depending on what you get. So we have 3 predictors. So this is going to be equal to 3. Degrees of freedom are additive. So this will be 29. So what you can gain from this is that the degrees of freedom for the total will always be, regardless of whether the number of predictors is p minus 1 or k, the degrees of freedom for the total is n minus 1. So guys, remember, sum of squares for regression, sum of squares for our error residual. These things are additive, so this number plus this number must equal this number. Remember, degrees of freedom are additive, so this number plus this number must equal that number. All right, gang, let's make it happen. Get our F statistics. So the mean square error, the mean square regression is just going to be 6861. I'm just going to grab the calculator here. 0.3 divided by 3. So we're going to get 2287.1. And remember that the mean square terms are not additive. So gang, I don't ever want to see you putting a value right there, because what we get by taking 15,771.2 divided by 29 will not be equal to 2287.1 plus this. Now, I encourage you to try that out if you want to do that, but all right, guys, what we need to do now is get our F statistic. And remember, our F statistic is just our mean square regression divided by our mean square error. So I'm going to take 2287.1 divided by 342.7. So give me a break on rounding error, or rounding, not rounding error, but we get an F statistic of 6.67. Okay? Now, what are we doing here? Here's what we're actually doing. What we're testing with the Anova table is we're testing H sub O that beta 0 equal beta 1 equal beta 2 equal beta 3 are all equal to 0. So none of the coefficients are statistically significant. If we reject the null, and I have no idea whether we're going to reject it yet or not, it's going to be based on our degrees of freedom with the test statistic of 6.61. So our alternative hypothesis is at least one of the b sub k's is not equal to 0. All right, gang, what we got going on here is we've got the F distribution, which looks like a positively skewed distribution. We've got our F statistic here, which is equal to what, 6.67? So our area to the right is going to give us our p-value. Now guys, we're going to use PF, but remember PF gives us area below. So area under the probability distribution will give us an area of 1. So again, going to be easy to do here. So we're just going to take that our p-value for F is going to be equal to 1 minus PF 6.67. Our degrees of freedom for the numerator were 3. Degrees of freedom for the regression was 3. Our degrees of freedom for the residual or the error term was 26. So guys, our p-value for the F is 0.0017. I'm going to write that down real quick. So at the 0.05 level, for alpha, we would reject the null. So what does that tell us? Well, that tells us that at least one of our betas, so we are rejecting this based on our data, this statement is more believable. So either LSS, IQ, and or EST appear to be statistically significant. Well, that's good. It leads us into the next part. I'll tell you what. Let's back up here. Before we get there, let's get into the descriptives. And the first thing I want to calculate is the coefficient of determination, which is r squared. Now this thing's really easy to calculate because it's just the sum of squares for the regression divided by the sum of squares for the total. And I forget what those are, but we can clearly go back and find those. So sum of squares for the regression divided by the sum of squares for the total is going to be 0.435. So this is going to be 43.5%. Now, what this tells us, the interpretation would tell us that we can say that 43.5% of the variance in read is explained by the regression on the set of predictors LSS, IQ, and EST. You might be the glass is half empty here and say that 56.5% of the variance in read is explained by something else, by other predictors. 43.5%, and I don't like these lines in sand. Statistically speaking, when you take good quantitative, you guys got into this with the likelihood stuff. When you take good quantitative data and you create lines in the sand and dichotomize it, we restrict the variation. And to me, that's a statistical dilemma. Not a statistical dilemma. It's a statistical nuance and a statistical screw-up to take a good quantitative measurement and dichotomize it. So I'm not going to do that here. Is it too high, too low? I'm not going to do that. It's just 43.5% of the variance in read is explained by the regression on our set of predictors. Now, we can show that as the set of predictors increases, our r squared tends to be artificially inflated. So, since we have three predictors, our r squared is probably, very likely, in fact, overestimating overestimating, did I get that right? Yeah. The variance in read that's explained by the set of predictors. So what we do there, and I'm going to scoot back over here to the air server. What we want to do there is we want to come in with what's called the adjusted R squared. Now, gang, when you're doing simple linear regression, when you've got one predictor, this is perfectly fine to calculate and throw all the eggs in one basket. If you have two predictors, there's not going to be a lot of difference between the adjusted R squared and the R squared in most cases. But when you get more predictors, this becomes the standard, the adjusted R squared. Guys, this is pretty easy to find. It's just 1 minus. I always remember it. All right, I always remember that the sum of squares for the total, the degrees of freedom go on the diagonal. And this is just the way I've always remembered it. The degrees of freedom for the sum of squares total goes up there. The degrees of freedom for the sum of squares for the error goes right there. So gang, if we can get this calculated, life is going to be just super, super good, right? So this shouldn't be any problem to do. Go back over. So we need the so the adjusted R squared is going to be 1 minus. So first of all, I need n minus 1, which is 29. And I need n minus p, which would be 26. And I need to multiply by sum of squares for the error, sum of squares for the total. The guys, the adjusted R squared is going to be 37.0%, or well, 36.99% if we go out two places. I think I'll do that. So the adjusted R squared is going to be significantly less. Not statistically significant. I've got to be careful with that. It's going to be quite a bit less, right around almost 6.5 units, yeah. So the adjusted R squared would be something that would be much better for us to depend on. So we would say that approximately 37% of the variance in read can be explained by the regression on the set of predictors, LSS, EST, and IQ. Now, guys, I want to show something on. I want to demonstrate something to you that's going to be a nuance. If we do the Anova table. Using R. So, guys, the best thing we can probably do here is first of all create our model. So our model is going to be, our linear model is going to be read tilde LSS plus IQ plus EST, right? So if we just do model, it's going to give us the coefficients, and you can see that the coefficients, line up with what we showed earlier for our beta. Now you can do a summary here for model, and it's going to give you some standard errors and our different things. And I encourage you to go back and look at the standard errors. I actually did those right, so I think I did standard error intercept. C32.6771. Again, what I'm focusing on right now are the standard errors. Forget just the center part. This part, the column under standard errors. The next thing I did was the standard error for, the standard error for LSS was 2.9978. We did the standard error for IQ, which was 0.2988. And you can see that everything is, of course, matching up, which is always cool. we've had some videos before where it did match up, right? So now, if you want to get fancy here and look at an Anova table, now what I want you to concentrate on is right here. When we did our statistic, our statistic analysis, we rejected the null, which said at least one beta is statistically significant, not equal to 0. Statistically speaking, we cannot determine that LSS is different from 0. Statistically speaking, we cannot determine that IQ is different from 0. But statistically speaking, we have reason to believe that the beta estimate for EST is statistically significant and different than 0. So, you know, we're going to demonstrate that in a second. Something else I want to show to you, it's a common mistake for a lot of people. They think the bigger this estimate is, the better chance it's got of being statistically significant. And it turned out in this situation where our largest estimate was the one that was statistically significant. However, if you look at the estimate for 0.4749, you've got to take in consideration that the t-value and the p-value are based on the standard error. So you could have a small estimate divided out by, you know, relatively speaking to the estimate, a larger standard error, and you can create a t-value that's, so anyway, you don't necessarily, the estimates that's the biggest here doesn't necessarily lead to statistical significance. And that's important enough to actually say something about it. For example, what if I wanted to predict first-year college GPA by taking an ACT plus SAT score? Let's say we have a group of students who took both scores, ACT and SAT, and we wanted to use those two scores to predict first-year college GPA. Now, if you think about it, the interpretation of these coefficients at the end of the day is controlling for the other one. If we increase SAT, ACT, whichever one we're focusing on, by 1 unit, the beta coefficient is the change in the first-year college GPA. So let's just say, for instance, that well, I don't want to put numbers in there because I don't know how it would turn out. Nevertheless, what I want you to focus on are the interpretations for, first of all, ACT. So if we were going to interpret the coefficient for ACT, we would say controlling for the SAT score, the predicted first-year college GPA will whatever the ACT is will increase according to what the coefficient is and for the ACT. It's kind of hard to explain without numbers there. SAT would be the same thing. We would say controlling for SAT, controlling for ACT, the predicted first-year college GPA will either increase or decrease the amount of the beta coefficient for SAT. Guys, at the end of the day, what I want you to focus on here is a difference in 1 unit the same for ACT and SAT? And absolutely it isn't. ACTs tend to range from about 6 to 36. SATs tend to range from about 200 to 800. A person with a, for example, 30 versus a person who has an ACT of 29, again, 1 unit difference, that's a completely different comparison than someone, for example, who has a 600 and a 601 on the SAT, just because of the unit of measurement. So let me go in and do the ANOVA. So this is going to absolutely drive you crazy. So if I do ANOVA linear model for the model, then we're going to get this. Now, I just want you to look at that. First of all, does that look anything like the Anova table that we created? Sorta. Sorta. Degrees of freedom don't look the same. However, we do have the 26. And if we add 1 plus 1 plus 1, we get 3, which, is similar. Sum of squares for the residuals, for the errors, 8909. Well, that matches up. And then we get this partitioning out of the, instead of just having one line of regression, what it's done is it's partitioned out the sum of squares for LSS, IQ, and EST. All right, no big deal. Trust me, if you add those three numbers together, 2023.8, 33.16, and 1521.4, you're going to get 6861.3, just like we got for the sum of squares for regression. Now is when the fun starts. What they do here is they create what's called a sequential partition of the sum of squares. And when you come out here and look at the p-values, you're going to see statistical significance, statistical significance, statistical significance. Yet up here, you're going to see not statistically significance, not statistically significance, and statistical significance. All right, gang, here's what happens. This breaks down the sum of squares in partitions. This looks at kind of a hierarchical modeling in a sense. This sets out, first of all, and looks at the sum of squares for LSS. This probability p-value out here talks about the sum of squares being statistically significant. IQ has the nature, if you will, given that LSS is in our model, the additional sum of squares of 36 is it statistically significant. Now, in my opinion, this ANOVA table in this form, which we're not going to get into it this class because I'm already running behind, but our second class that I'm going to teach you guys either next summer or whenever we decide it's going to be, that's going to be the first thing we're going to talk about, is partitioning out the sum of squares. And it actually becomes very helpful in making important decisions. But guys, at the end of the day, what I want you to see from this is incredibly difficult to interpret in terms of estimating our coefficients, which we can do up here, which actually looks at the impact of one in consideration of the other three being in the model. It's not what's going on here. IQ is considered with LSS already being in our model. The sum of squares for EST is calculated with the consideration that LSS and IQ are already in the model. So it's a sequential calculation of our F value and our probability. Guys, at the end of the day, we don't rely on this to make decisions that we're interested in right now. Okay, now that that's completely and utterly confused, we want to start now looking at, hold on. Sorry. All right, well, the gang just got home, so it's going to get loud. So the next thing I want to do... The gang. Yeah, you're the gang. So the next thing I want to do is look at the inferences. And all I'm going to do here is I'm going to just look at the inference for for IQ.
What?
Now, remember, guys, for inference, we need the test statistic. And the test statistic is going to be the beta for IQ.
The what I got
I'm sorry,
here?
the B for IQ minus the beta for IQ over the standard error for the beta for IQ. And since we are going to be
Looks like it
testing
says
here,
It looks like it says bit IQ.
that our beta IQ is equal to 0 versus H sub A, the beta IQ not equal to 0, then we are going to have right here that equal to 0. So ultimately, guys, what we're going to have is we're going to have that our coefficient estimate, beta for IQ, over the standard error for beta IQ. Well, keep a running total here. We can go back to R. And what was our beta estimate for IQ? Well, we got that back there when we calculated B. And remember, the first was our intercept. The second was LSS. So 0.475 was the beta estimate. And we saw that we could find the standard error for IQ by 0.29. Well, let's just call it 0.299. So guys, what we're going to have, actually I want to stay here. So our T for IQ is going to be equal to the beta 0.475 divided by 0.299, and we get TIQ is 1.58. Notice that corresponds to our T of 1.589 right up here. And I'm going to go ahead and write that over on the chalkboard too, so we don't. Okay, now what we got to do is we got to calculate our p-value. You guys struggled with this a little bit on assignment number 1, so let's go back over here and talk about what this is. We're going to have degrees of freedom, a t-distribution, and we have 1.589. And we're going to look at the area above, but we have to multiply by 2 because we're doing a two-tail test. Yeah. Guys, this whole PT is going to give us area below. So what we have to do is take 1 minus and make the calculation. Now, for these calculations, the degrees of freedom are going to be let's see, our degrees of freedom for the estimates will be well, I forget. What are the degrees of freedom for the T? I'm pretty sure it's n minus 2 because we would have 2 degrees of freedom because we use, yeah. So guys, what we're going to do is we're going to do our p-value for IQ. And this is going to be equal to 1 minus PT of 1.589. Degrees of freedom, we have sample size of 30, so we'll do 28. So p-value for IQ is 0.06. That's not going to be Oh, I forgot to multiply by 2. So I need to take the p-value for IQ and multiply by 2. And you can see that we get not the right thing. Okay, let me think this one through, guys. We need, so we have found a t-distribution, which is a chi-squared. Let's see. So we're actually going to need, so our p-value for IQ is actually going to have to be calculated this way. So we're going to have 2 times 1 minus PT 1.589, comma 26. Yeah. So make a note, the degrees of freedom for the test statistic is n minus p when we have p minus 1 predictors, or it would be n minus k minus 1 when we consider k predictors. So guys, here if we have p minus 1 predictors, then p is going to be 4, so 30 minus 4 gives us 26. And again, if we have k predictors, which would be 3, we would have 30 minus 3 minus 1, which is also 26. So just however we look at that, that's going to be our p-value. And you can see that it matches with our p-value up here. Now, you might be saying, well, sure doesn't match up with our p-value down here. It's not going to. Again, this is the Anova Table. This is our analysis of variance for the regression. Here we're partitioning out the sum of squares and looking at the p-values for that. That's something completely different than what we did before. All right, gang. So we've got our test statistic. We've got our p-values. We've looked at at the inference. So the next thing I want to do is I want to look at the estimate the mean response. So let's say, for example, that we want to focus on the level where someone has a LSS of 5, an IQ of 110, and an EST of, I don't really even remember what these things were, where they were even close to be honest with you. Let's go back and take a look at this. So that would be, let's say that they have an estimated reading level of, who knows, 4. I'll tell you what, let's actually bump up there to a 7. Now, what we can do is we can get a mean response for these values. But gang, what you got to appreciate is if we, for example, brought in 100 kids with an LSS of 7, an IQ of 110, and an estimated reading level of 4, each kid would very likely have a different reading score. So what we're going to do is we need to look at the mean response, and obviously we need to look at the variation. Okay? Now, this gets a little crazy. Nothing actually too awful crazy, but so the first thing we're going to have is we're going to have our okay. All right, guys, let me think about this one for just a second. Lost my train of thought here. All right. So let's take this, which we know is going to be found by taking x times beta. But x in this case is going to be 1 x in 1, x in 2, x in, and let's just call it p minus 1, okay. So for our problem, we're going to have x is going to be equal to 1, 7, 110, and 4. But in this case, our beta matrix is going to be a 1 by 4. Our x matrix is going to be a 1 by 4. So what we're going to have to do is we're going to have to take x transpose, which makes this a 4 by 1. Times beta. Yes. All right. So let's get back into R. Equal 4. So we'll call y mean. So the mean response for this is going to be found by okay guys, I'm losing my, so I need to make this let's call it x mean response. Now guys, I'm drawing a complete and total blank here, what we need to do. It's obvious what we need to do if we've got our regression model, but so if we take x is a 1 by 4, beta is going to be a 4 by 1. All right, let's call this x mean, and let's just let this be 1, 7, 110, and 4. Now what I want here is my x mean vector, and I want this to be matrix x mean in row equals 4, in column equal 1, and by row equal false. So x mean is what we want. So we want, so our y mean predict is going to be the transpose of x mean times our beta. So y mean predicted is going to be 68.3789. Now, you know, this is going to be the same thing if we had done it the other way. You know, and that's just simply put 7, 110, and 4 in our model and come up with the predicted mean. Now, it turns out that the variation for the predicted mean, let me go back and get this. Turns out that the, I can remember it, for the mean response. Which will be given to us in terms of the variance. It's going to be the mean square error times x transpose h times x transpose x inverse x h. Now remember, this is from before. And of course this is going to be our, I forget, what did we say, 7, 110. And 4. So let's calculate the standard error squared. So now we're going to run into problems multiplying by the mean square error like we did before. So let's just let's just do this. So let's take, we called this what, the transpose of x mean, right? Yes. Times, now I need to go solve and transpose x. X. And then I need to go times x mean. So then I need to take SESQ. No, it's not going to do this. Let me do the mean square error times SESQ. Oh, wow, it actually did. So the standard error here is going to be, well, the standard error squared is going to be 28.2, or I'm sorry, 28.87. So if I can take the square root of this, 86873, I get 5.371. So guys, finally, we are now set. So we're now set to create the 95% confidence interval for the mean response. when we predict read from, and LSS equal to 7, IQ equal 110, and EST equal 4. Okay, so let's do this. Now guys, remember, what do we do in a confidence interval? We take our point estimate plus minus our T critical times our standard error. So we've got our point estimate. That's going to be the mean response, which we found to be 68.3789. We've got the standard error, but what we now need to do is we need to now come in and find our T critical. All right, well, that's going to be really easy to do. We can just do this with QT. And QT, we want for a 95% confidence interval, the lower bound is going to have 0.025 area below, and we have degrees of freedom, n minus k minus 1 or n minus p, which is 26. So QT is going to be this. So boys and girls, what we can do is we can take 68.38 minus 2.06 times the standard error, which is 5.37. Then probably, I'm just going to copy and paste this, if it'll let me. And I can just change that to plus, and I get this. Therefore, our 95% confidence interval for the mean response for LSS equals 7, IQ equal 110. So for all those kids out there that has LSS of 7, IQ of 110, estimated reading level of 4, the 95% confidence interval is 57.3 to 79.4. So there's a 0.95 probability this interval contains the mean response for